So now we're going to continue talking about ways of solving for parts of triangles, but rather than being able to use SOHCAHTOA, Pythagorean theorem, or our special right triangles, we're going to look at non-right triangles. And if we're missing side lengths or angles, we have two different laws that we can use, law of sines and law of cosines. Okay, so the first one we're going to talk about is the easier one, and the preferred one when we can use it, called law of sines. Okay, so law of sines is used for non-right triangles where we know at least one angle and the side opposite it. So, and one side opposite our known angle. So if we say in this triangle, if I knew the angle at B, I need to know at least the side length B and one other piece of information. And you'll be able to see why when we start to set this up. Essentially, we're going to set up a proportion problem, and we need to know 3 out of the 4 pieces in order to solve that way. So, all right, but we need to know at least an angle and the side opposite it to use law of sines. Okay, so how law of sines works is the sine of our angle at A over its side length, the opposite side A, that ratio is the same ratio as the angle at B is to side length B, and the same ratio as the angle at C to side length C. So those ratios are all the same. Now we're never going to set one up that has all 3 like this, but we're going to set up a proportion problem from them. So let's take a look at our first example here. Find the missing angle or side length, round to the nearest tenth. Okay, so to solve for this missing length, BC, if you want, we can call it X, or since it's opposite A, we could also call it little a, right? Side length A. So here, we do know one angle and the side opposite it, right? 54 degrees, and its opposite side, 35. So here we can say, and it doesn't really matter if you follow this exact format, but we can set up this ratio. The sine of our angle, 54 degrees, is to its opposite side, 35, as, here's the angle opposite the side we want, 97 degrees, so the sine of 97 degrees is to the missing length A. Like those ratios, the sine of my angle over its opposite side will equal the sine of any other angle in my triangle to its opposite side, as long as we stay within one triangle. So as you can see, we essentially have a proportion here, and we're just going to cross multiply. So A times sine of 54 is A times the sine of 54 equals 35 times the sine of 97 degrees. Sorry, sine of 97 degrees. Okay, now to finish getting A by itself, note that it's being multiplied by the sine of 54 degrees. So we simply divide both sides by the sine of 54 degrees. And then here, we now have a value that should equal A, right? Or an expression that equals A. So we need to go to our calculator. Okay, so let's type in / for our fraction 35 times the sine of 97. Again, check to make sure your calculator is in degree mode. So on Desmos, you should be able to read degree there, over the sine of 54. And that tells us our side length A, which appears to be opposite the largest angle, and should be therefore the largest length in our triangle. And that seems like a pretty reasonable value. It's 42.9 if we're going to 1 decimal place. So A is approximately 42.9 centimeters. Okay. All right, let's try B. Pretty similar problem. Now note here, we only know one side, but we immediately don't know the angle opposite it. Well, hopefully remember, the 3 angles in a triangle should add up to 180. And if we know 2 out of the 3, we can say, hey, my unknown angle at C plus 49 plus 63 has to total 180. And of course, we can use that to solve for our angle at C. So subtract those two values from 180, take away 49, take away 63, and our remaining angle is 68 degrees. Sorry, it's a little off the screen there for you. 68 degrees. All right, so we now know the angle at C equals 68 degrees. And we can fill that in. All right, well now we actually do know an angle and the side opposite it. So we should have enough for law of sines again. Okay, so let's set up that ratio. Sine of 68 degrees is to its opposite side, 27 centimeters, as, and it's asking me to find AC. So this length here, which is opposite B, we could call this lowercase b. So we're going to say sine of that angle, 49 degrees, to our missing length b, or x, or whatever you'd like to call it. But once again, we're going to need to cross multiply. So b times the sine of 68 degrees equals 27 times the sine of 49 degrees. And then to get b by itself, we'll divide away the sine of 68 degrees on each side. And so now we have an expression, or we can go to our calculator and find our value for b. So let's go type that in. Okay, so we got it all typed in there. 27 times the sine of 49 degrees over the sine of 68 degrees. And again, the calculator knows it's in degree mode, so it knows those angles are degrees. And rounding to 1 decimal place, well, actually, because of this 7, we need to round that up, that 9 to a 10, which moves that up to a 22. So the way we'd write these answers, we'd say b is about 22.0 centimeters. And that extra 0 may not seem like it's necessary, but it is telling whoever's reading our answer that we went to the accuracy of the hundredths place, or sorry, the tenths place, and then it just happened to round to a 0. It's not exactly 22, but 22.0 is what we rounded it to. Okay, these next two are kind of similar, but this time we're going to be using law of sines again, but this time to find an angle. And again, a good way to know to use law of sines here is these are non-right triangles, and we do know one angle and the side opposite it. So let's go ahead and start by just setting up that ratio. Sine of 66 degrees is to the opposite side, 23, as, and it wants me to find angle B. Okay, so this is my unknown angle here, and it's opposite the length of 13. So the sine of angle B is to 13. Okay, so once again, we are going to cross multiply. So we get 23 times the sine of B equals 13 times the sine of 66. Okay, well, I need to get sine of B by itself, so we're going to divide away the 23. And then lastly, to get to get B out of the sine function, like we did before, we need to use the inverse sine. So I'm going to leave a little bit of space so I can write that over here as well. We need to do the inverse sine of both sides, or arc sine, whichever way you'd like to call that. So we would do the inverse sine of this side. We'll technically just cancel out sine, but we do need to type this whole thing in our calculator at the right. So this will get me b equals this expression. Let's go to the calculator. Okay, so in Desmos, the inverse sine is under function, this little function tab, inverse sine of our fraction, which is 13 times the sine of 66 degrees. Again, make sure it's in degree mode, which it is because I can see degree, over 23. And it's giving me the angle approximation back for our triangle. That angle, and looking at it, that seems reasonable. It's about 31.1 degrees. Going to the nearest tenth there, about 31.1 degrees. Okay, follow that example, see if you can do D here. Go ahead and pause the video and try this out, and unpause when you're ready. All right, if you set this up correctly, you should have sine of 96 over 34 equals the sine of A over 29. Cross multiplying, dividing by 34, and doing the inverse sine or arc sine of both sides gets us A equals this expression, which according to our calculator rounds to 58.0 degrees. All right, so now we're talking about law of cosines, which is when we don't have enough information to use law of sines. So there's really kind of 6 formulas here, but you really only need to kind of memorize one of them. This tends to be the one I memorize for when you're solving for a side length. You could even find alternate versions of these, of course. When you're solving for a length like c, and this formula equals c squared, you will need to do the square root of each of these. And since c is a length, we only want the positive case, so you don't need to do plus or minus. These are just if you're solving for an angle. So if I'm solving for the angle at, say, C, right, like say C in this triangle, this is just this formula rearranged to get C out of cosine. So you subtract the A over, subtract the B over, divide away the 2AB, so subtract A over, subtract B over, divide by negative 2AB, and then to get C out of cosine, you would need to do the inverse cosine of both sides. And so that's where these formulas from the right come from. It's really just one formula applied 3 different ways, I guess. And then these are for angles, which is just manipulating this formula. Anyway, let's find some missing lengths here. Find the length of BC. So we can call this lowercase a if you'd like, because it's opposite side A. Now, again, I do know one angle, but I don't know the side across from it. So this is why we cannot use law of sines. So since we're solving for a, we'll go ahead and use this top version. A squared equals b squared plus c squared minus 2bc times the cosine of the angle at A. So plugging in here, what do we know? We don't know a squared yet, of course, but we know b squared. So this would be b, right? 28 squared. And it doesn't actually matter which one of these is technically b or c, because the operations that we're going to do to both of them will be the same, essentially. We're going to square them and add them together, and then subtract 2 times each of those values. So if you put them in a different order, it won't make a difference. So minus 2 times b times c, 28 times 25, times the cosine of the angle at A, which is 66 degrees. Now again, to finish solving for A, we're going to need to do the square root. That's a pretty terrible symbol, but hopefully you get the idea here. Yeah, I can't do that. All right, there we go. So now we want to type that into our Desmos calculator. So the square root of 28 squared plus 25 squared minus 2 times 28 times 25, oops, if I can type, times the cosine, holy moly, come on now, times the cosine of 66 degrees. So I'd probably make this a little wider here so we can fit it all on the screen. And make sure your calculator, of course, is in degree mode, so your calculator knows 66 is degrees and not radians. And it tells me my missing side length, which seems pretty reasonable here, is about 28.97, which if I'm rounding to the nearest tenth, means we need to actually round this up to 29.0. So A is approximately 29.0 kilometers. Pretty big triangle. All right, our next one, we're going to need to do kind of the same idea. In fact, this would be a great one for you to try out and see if you can find side length AC or lowercase b. So again, when you're setting up this formula, the side length you're looking for squared equals the other 2 sides, like all of this part is the other 2 sides, and then cosine of the angle opposite your side. So if you kind of remember that pattern, you don't need to like memorize all 3 of those, etc. So anyway, try problem F, unpause the video when you're done. All right, so you should have come up with about 12.6. Our missing side is 12.6. So you can see all of that typed into Desmos here. Here was our equation, and there's our answer, 12.6 centimeters. Okay, now next we're going to look at a few examples where we'll need to use law of cosines to solve for a missing angle. Okay, so on our next one here, we're going to need to solve for a missing angle. So notice we have a non-right triangle. We only know one angle, but we don't know the side opposite it. So in order to solve for any of these other angles, we're going to need law of cosines. However, to use law of cosines, if you notice, we need to know A, B, and C. In other words, all three side lengths. And right now, we don't know side length A. So in fact, before we can find this angle, we need to do what we just did in the previous two problems as an extra complication here. So we need to find this. So let's do that first. To find side length A, we know A squared equals B squared plus C squared minus 2BC times the cosine of the angle at A. Okay, so let's plug in and find A. All right, so we're plugging in for our other two sides, 18 and 22, right, in our formula, and cosine at 58 degrees. And that tells me my missing length, rounding to one decimal place, is about 19.7. Okay, so now we have enough information to solve for the angle at B. So we can go straight to this formula. Again, this is just this same type of formula manipulated to solve for A and get A out of cosine. So we can go ahead and use the one that's labeled as B. So B here is equal to the inverse cosine or arc cosine of B squared, so side length B, which we'll call this one and this one. So 18 squared, it's the side opposite our angle, minus the other two sides, 19.7 squared and minus 22 squared, all over negative 2 times A. These are the other two sides here, so 19.7 and 22. So I need to do the inverse cosine of all of that. So in Desmos, your inverse cosine is under function again. So inverse cosine, press / for your fraction, 18 squared minus 19.7 squared minus 22 squared, all over, all over negative 2 times 19.7 times 22. And it tells us our angle going to one decimal place is about a 50.8 degree angle. So it's about 50.8 degrees. So angle B is about 50.8 degrees. Okay, so our last one is actually very similar to the one we just did here. Again, we're given an angle up here at B, but we don't know the side opposite it. So we know we can't use law of sines. And to find the missing angle, we need to know all three sides. So you're going to need to find this side length first, again, using the formula like we did in the previous three problems. And then you can use one of our angle variations to find the angle at C. So go ahead and try that out, pause the video, and unpause when you're finished. All right, you should have come up with hopefully a side length of B of approximately 25.6 rounded to the nearest tenth. And then using that value and plugging into, you could use this version if you wanted to follow the A, B, and C exactly. But for finding the angle at C, it starts off with the side length opposite it squared minus the square of the other two lengths of each of those, and then all divided by negative 2 times the other two lengths. All of that inside of our arc cosine. So here's the Desmos. To double check both the length of 25.6 and the angle of 52.4 degrees for our final angle. Okay, we'll definitely do more problems like this in class. Make sure you ask questions if you're unsure.